How's it going, guys? In this video we're going to go over solubility and how to solve solubility curve problems. So first of all, what is solubility? It's the degree to which a substance dissolves in a solvent to make a solution. That's usually going to be in grams of solute per liter of solvent. So how does temperature affect solubility? Basically, the best way to think about it is just up here. An increase in temperature always shifts equilibrium to favor an endothermic process, and that's going to be different depending on which phase of matter it's in. So for solids, the solubility will tend to increase with temperature, and for gases, it's going to be the opposite. Solubility will decrease through temperature. So I'm going to show a quick demonstration here, and then we'll jump into some problems. So in this first one, we're just comparing the solubility of a sweetener in water versus olive oil in water, and the water is at the same temperature, and it's pretty stereotypical. As you can tell, the olive oil is pretty well defined from the water versus the sweetener. It's already dissolved, and you can't even tell that it's in there anymore. It just shows the difference in solubility. Now here we have cold water and hot water, and this about the same amount of paint in each of them, and as you can tell, obviously the hot water increases the solubility because it's higher temperature. But I think it's interesting, you can see on the hot water the paint is like misting off of it, versus in the cold it's coming off in like defined specks, which kind of another way to indicate the solubility here. This one I repeated it, but I added the paint first and then the water, and as you can tell from the cold, it wasn't even going to take on the color of the paint until I disturbed it, and even then it's significantly slower, and the pieces coming off are more well defined. So here we have just 6 different problems that we're going to use these solubility curves to answer. Alright guys, so I'm going to start going through each of these problems one by one using these charts here, but I wanted to pre-write them out in case anyone wanted to try to attempt them and then check their answers after. So I'll just move down so you can see all 6 of these. And if you're going to do them on your own, then I'd pause now, and then I'm going to start going through them now. So first of all, approximately how many grams of KNO3 will dissolve in 440 grams of water at 50 degrees Celsius? So the first thing I look at is at 50, we have 80 grams will dissolve in 100 of the KNO3, because we're looking on this chart here, KNO3 right there, and we're at 50 degrees. It's right here. Just follow that line up. It's right at 80. So we have 80 grams. So now we just set up a proportion. So we have 80 grams over 100 grams, and that's of the KNO3, and that's per 100 grams of H2O, and that's going to be equal to X grams KNO3 per 440 grams of water. Now we're just going to do that calculation. We're going to cross multiply and divide, and we're going to get, should have left more space here, 352 KNO3. Alright, moving on to number 2 here. So how much NH4Cl will dissolve in 50 grams of H2O at 80 degrees? So first of all, we'll just set this one up again. So NH4Cl, we'll find it on the chart. What temperature we're working on? 80 degrees. So 80 degrees NH4Cl. Looks like we're right at 65. So we're going to do 65 grams at 80 degrees of NH4Cl per 100 grams of water, and that's going to be equal to 50 grams water. And this one I think you probably can just do really quick in your head. Really you're just going to divide it by 2 essentially. So what we're going to get is 32.5 grams of NH4Cl. Perfect. Okay, so now we'll move on to number 3 over here. Let me scoot this down. Alright, so you have a 50 degree solution of 200 grams of water and 20 grams of KClO3. How many moles of KClO3 could you dissolve in the solution if its temperature was raised to 80 degrees? So it's a little bit, it seems a little bit more complicated than the other ones, but it's really not too bad. So we're going to start by kind of doing what we always do. So what are we looking at? So the temperature is 80 degrees. So at 80 degrees Celsius, and we're looking at KClO3. So KClO3 right here, 80 degrees. Look up, and that is right at 40. So at 80 degrees, 40 grams dissolves in 100 grams H2O. So now what we're going to do is we're going to take 40 grams. We're going to do 40 times 2 equals 80 grams. And what we're going to do is KClO3 per 200 grams of water. H2O, sorry. So then what we're going to do is we'll take 40 grams KClO3 and then multiply that by 1 mole over 122.55, the molar mass, and we're going to get we're going to divide it by the molar mass, right, to get the molar mass, 0.326 mole of KClO3. So it's asking again, we can double check how many moles of KClO3 could you dissolve, and we're going to have that as our answer. Alright, cool. So now we're going to move on to number 4. How much NO can be dissolved in 350 grams of water at 30 degrees Celsius? So again, we're just going to say we're looking at 30 degrees and we're looking at NO. So that's on this chart here. So we have, and another thing to look at here, these charts, let's move up here. These two charts are, I try to color code them so it's easier to see, but for this one, for the gases, these are all gases and these are solids. The solubility you have to make sure you check is in milligrams as opposed to grams. This one's all in grams. It's still grams per 100 grams of water, but it's milligrams of solute, so it's a lot smaller. So here we have at 30 degrees, so we're looking at the temperature, temperature down here, 30 degrees, and we're looking at NO. That's going to be between the 4 and the 6, so it's going to be 5. So at 30 degrees, we have 5 milligrams of NO per 100 grams of water. And that's going to equal X over 350. And then we're just going to cross multiply and divide. Okay. 17.5 milligrams of NO. Not too bad. So now we're going to move to number 5. So I'm just trying to center this here. How many grams of O2 can be dissolved in 42 grams of water at 40 degrees? So again, we're looking at 40 degrees. So find the 40, go up. It looks like for the green line there, that is between the 2 and the 4, so that's going to be 3 milligrams. So now we can say at 40 degrees Celsius, we have 3 milligrams per 100 grams of water, O2. And then we can set up that proportion. It's going to be X over 42 grams of water. And we'll just cross multiply and divide. Okay, so we got X equals 1.26 mg of oxygen. That is not our final answer though, I believe, because how many grams of O2 can be dissolved? And that's what we just found is milligrams. So that's something that would be really easy to miss, I think. I kind of just try to throw that in because that's something that will trick a lot of people. Not trick might be the wrong word, but just might catch them off guard. So we have 126 times 0.001 grams per milligram on the bottom, so our units cancel. And we're just going to do that metric conversion. And I'm trying to save room, so I'll put the final answer up here. We're going to end up with 1.26 times 10 to the negative 3 grams of O2. In other words, 0.00126. All right, cool. So now we're on to the last problem here, number 6. A solution of N2 is in 300 grams of water is at its maximum solubility at 15 degrees Celsius. In other words, it's where it is on the line. We're going to get into that in the next video here, but it's saturated to be at its maximum solubility. So how many more milligrams of N2 could dissolve in the solution if the temperature was lowered to 5 degrees Celsius? And again, we can go all the way back to this part here. We know for gases, as the temperature increases, it's going to decrease solubility. So in other words, decreasing the temperature should in turn, if you decrease the temperature, it should increase solubility of gases. So now we're going to see that kind of in action here. First off, what we're going to do is we're going to say at 15 degrees Celsius, and we're looking at N2. So at 15 degrees, we have, looks like 2 milligrams. So we have 2 milligrams of N2 over 100 grams of water equals X over 300 grams, because that's what we're looking for. So then we just cross multiply and divide. And this one you probably also do in your head, but it's going to be 6 milligrams of N2. And now we're just going to plug that in at 5. We're going to look again. And it's going to be a little bit more. It's going to be 2.7, we'll say. 2.7 milligrams of N2 per 100 grams of water. It's going to equal X over 300. And we can get 8.1. So we just found the two, basically we just tracked two different spots on the solubility curve, but we're just going to take the difference because it says how many more milligrams of N2 could dissolve if the temperature was lowered. So how many more, it indicates that it's a comparison. We're just going to have the 8.1 minus 6, so we're going to end up with 2.1 mg of N2 more. All right, cool. So that's the last problem I had here. And yeah, we'll just go back to this stuff here. I think that the take-home point here is an increase in temperature always shifts equilibrium to favor an endothermic process. And then you can kind of read these descriptions here for why each one is that. But basically, for solids, increasing in temperature should increase the solubility, and for gases, it should be the opposite. And that's not always the case, but you'll find it is the case most of the time. All right, cool. I hope this helps someone.